All right, let's begin. So you have a homework assignment on your plate right now. It's due before class on Wednesday. So hopefully you've got an early start on that one, working through it. If you have any questions, you can always stop by during my office hours. I'm happy to help you out. I haven't yet graded the quiz that we did in class on Friday, but I will return that to you in class on Wednesday. We were kind of moving pretty quickly on Friday and didn't get to finish our discussion about gradients. And gradients are complicated, and so I don't want us to skip through it without completing in-class exercise number 8. So that's what we're going to do today, is we're going to pick back up on problem number 3. Hopefully you still have that handout from Friday's class. After we finish in-class exercise number 8, we're going to discuss finding the unknown interest rate and the number of periods. And so, we've already done problems where you find A given P or find P given G. But what we're going to now transition into isn't when the amount is the unknown, but how do we solve it if the interest rate is the unknown, or if the number of years is the unknown. So that's what we're going to start on today. Any questions? All right. So on in-class exercise number 8, before I move on to that, tonight is that free dinner that I was talking about earlier. It's an information session hosted by the Division of Highways. So I'd encourage you to consider, if you don't already have an internship lined up for this summer, consider stopping by room 1203 at 5 o'clock, because DOH is going to be talking about their summer internship program, and they're also providing some food. Although I don't know what, I would assume it's probably pizza, right? That seems to be the default.
Most likely.
It's not going to be filet. Yeah. All right. So tonight, 5 o'clock. All right, so turn to in-class exercise number 8. On the third problem, this is the cash flow diagram that you see. So we're trying to figure out what's the present value of some series where in the first year you have to pay $400. In the second year you pay $430, and each year after that you have to pay progressively $30 more each year. Now that's not just a gradient, it's a gradient and an annual series on top of each other. So they're combined. And so that's what I've done here, is I've separated those two components out. So we have the gradient component where you're find P given G, and G is 30. And then the annual series component is find P given A, where A is 400. In that handout, I asked you to do it according to the equation method. Now, just in case you don't have the handout from Friday's class, I'll write both of the formulas here on the whiteboard. But what we're trying to do is find out what is P for the given G and the given A. All right, so let me start writing that formula on the whiteboard, and maybe you don't need it because maybe you have the handout and the equations were on the first page of that. But we're going to use the equation method to find out what is the total present value, the present value of the gradient component and the annual series component. So if you're not sure where to start, a good beginning point is just substitute in I and N into both of those equations and find out what is the factor that you're going to have to use. And so I is 0.12, and then N for both of these is 5. The N, even for the gradient, includes year 1 where you don't see the first extra amount being added. So N equals 5 and I equals 0.12. So substitute those in and find out what is the factor that is the ratio of P to either A or P to G. Okay, so we have both an annual series and a gradient on the same figure. And the idea is we need to separate them out before we can find out the present value. And so what I'm illustrating here is, here's the gradient part of it, where it goes 30, 60, 90, 120. We want to find the present value of that. And then we also want to find the present value of the annual series, which is a constant 400 each year. So, like, the real world interpretation of this is, if you were going to get some money today in year 0 so that you could afford to pay out this series in the future, and the interest rate is 12%, meaning you're going to take the money that you get today and put it in a bank that pays 12% so that you can cover these future liabilities, how much would you have to receive today for it to be economically equivalent? You know, taking into account the interest and the time value of money, how much should you get today in order to agree to these future liabilities? Okay, so that's the real world interpretation. Now, how do we find the P? Okay, solving for the factors. Here's the formula for find P given A. And you'll notice that I do the substitutions really deliberately with a lot of steps. I don't just put it into the calculator and hope that I put all the parentheses in the right spot, because it's so easy to make mistakes. So if you write it down, you write down what are your substitutions, and then intermediate, like combining things together, it makes it easier to double check your work along the way. And so in an exam, you should always check your calculations, and having this intermediate step would allow you to double check the numerator, double check the denominator, double check the final answer, and so on. And so the present worth of the annual series, that $400 each year for 5 years, you should take $1,441.91 today in order to have enough to cover those 5 payments of $400. So if you put $1,441.91 into the bank today, and that bank is paying 12% interest, then you can afford to pay out $400 every year for 5 years. So that's the first component of the cash flow diagram, is that constant 400 that appeared in each of the years. Now the next part of it is the gradient component, and you can see I go through the steps of calculating the ratio for the gradient, and this formula is even more complicated, so I feel like it's a good process to calculate these steps separately and write down the intermediate steps. And so you get the ratio, the P to G ratio is 6.397. And so you multiply that ratio by G. So if G is down here in the denominator, if I move it to the right side, that just means I can multiply the $30, which is G, by the ratio, and that tells me it's $191.91 that I'd have to get today to be economically equivalent to this gradient series over time. And then combining the two components together means it should be $16.33 and 82 cents. Let me zoom out so we can see it all at once. All right. Seems weird, but it'll come second nature for you. And I'll start to get even more tricky, where this time n was the same for the gradient and the annual series, but I could have made it so that it was 400 for several years and then the gradient kicked in. And so if the 400 was going for several years before the gradient, then n would be different for the annual series than it would be for the gradient. So we'll do some complicated cash flow diagrams in the future, and it'll kind of be like a puzzle in a way. But for now, are there any questions on this specific example? All right. So that's just to close the loop on in-class exercise number 8. Now, what we're going to talk about today is finding the interest rate. So till now, we would be given an interest rate, and then one of the amounts was the unknown. But what we'll do instead is we'll solve for I. And The unknown interest rate is the interest rate that brings balance between the future values and the present values. And so here's just an illustration of the concept of balance. Here's another illustration of the concept of balance. And what we mean in economic terms is very specific. We mean that the present value of the inflows and the outflows is equal. If we have some cash flow diagram of payments over time, if we take all of those amounts to the present, then what we're looking for to achieve balance is what is the interest rate that makes the inflows and the outflows equal. That's how we know when we have the right I value, is it's the interest rate value that makes the inflows and the outflows equal. So the sum of the present value will be equal to 0. So keep that in mind as we go through this method today. So let's say that we pay out $23,000 today, and then we receive 6 annual payments of $5,000 each year. There is some interest rate that makes those equal. Now, it's not 0, right? If the interest rate is 0, then that means the future amounts have the same value as present amounts. And it looks like $30,000 is the aggregate total of dollars that's coming back. And so there's some interest rate that makes it so there's equilibrium between the value of the inflow and the value of the outflow. And what we're talking about by value is the economic value when the time is taken into account. So the cash flow diagram is balanced when the present value of inflows and outflows are equal. So we solve for the interest rate that causes that. Right now it's not yet known. So you'll be given a cash flow diagram, and you'll discount all of the future values to the present. This is the method. And then you combine it with the amount that's already at the present, and then you keep changing the interest rate value until the two numbers are equal, meaning that the outflows and the inflows are the same. That's the method that we'll follow. Now, we're going to use Microsoft Excel for a lot of these calculations as we do cash flow diagrams moving forward. And there's a funny thing about what Microsoft Excel does. There are some built-in financial calculations that it knows, like it has a function called PV, where it finds the present value for you. When you use the PV function, it automatically assumes that if you give it a positive number in, it should give you a negative number out. Because Excel is assuming that if you put into the function a positive value, then that means an inflow, and so what it will calculate is the outflow equivalent. So sometimes that's what we want it to do, sometimes we don't want it to change the sign. There may be certain situations where what we want to find is the magnitude of the present value, but we don't necessarily want Excel to change the sign for us. It does it by default, that's the convention. And so I'm telling you this because sometimes we're going to have to put in a negative sign into the function to kind of like override its predisposition to change the sign on us. So I'll try and give you that reminder until it becomes a habit. But just based on the assumptions that Excel makes, when we use its built-in functions, sometimes we have to override that assumption. Okay, so the in-class exercise I have for you today, let me open it up here on the screen so that you can get a look at it. Not that one. All right, the first thing that we're going to do is we have the assumption of you bought equipment for $60,000, it gives you income each year for 5 years. And then I'd like you to use the tables. There's some cash flow tables that are provided, the 10% table and the 12% table. Solve for the present value using the 10% and using the 12%. And then once you've done that, I'm going to show you on Excel how to solve for the unknown rate. So the unknown interest rate, here's a hint, it's somewhere between 10 and 12%, as you'll see as you start doing the calculations. Okay, so when you get the paper, the first thing you're going to do is sketch the cash flow diagram for the statement that's given, and then find P for the two interest rates, and we have the factor tables there on the handout. There's an important phrase here in italics where it says net present value. That means what's the value of your cost and the revenue that you're getting back. Combine it all together in year 0. So you're going to find the P given A for the 16,000. And it's going to be a different amount if it's 10% versus if it's 12. But whatever the amount is, combine that P that comes from the A along with the initial purchase price, which is also at time 0. So the net present value means put everything together and find the total value. I've got the solution up on the screen if you want to check to see whether you're headed in the right direction. If we discount the cash flow at 10%, this project is profitable, which means that your investment of $60,000 now, you're investing $60,000 so you can get $16,000 a year for 5 years. Well, let's say if you borrowed the money at 10% interest to do that, then the project is going to be profitable because you get to keep $652. That's the present value of your profits after you've covered the payback on the loan. However, if you borrowed money at 12%, this project isn't profitable. What it shows is if your interest rate is 12%, then those the future revenues aren't as valuable. You're having to discount the future revenues at a higher interest rate, and it doesn't cover the cost of the initial purchase. And so the net present value is negative when we have that 12% interest rate. Okay, so balance. What's the interest rate that would bring the future revenues and the present costs into balance so that the present value of all of it is in equilibrium? So what we're solving for is we want to find what I value makes the sum equal to 0. So there's some interest rate out there that will make these future revenues equal in value to the unknown present value. Now, before I do the Excel demonstration, are there any questions about the hand calculations part? Okay, so here in Excel, just observe for now. You will get onto the computer in future classes, but for today I just want to do a demonstration where what I'm going to have is here an interest rate, and to start off I'm going to put in one of the numbers we already know. So I'm going to put in 12% interest just to make sure that this is functioning the way it should, because we know when it's 12% interest, then the present value should be negative $2,323. I'm going to have the year, the amount, and then the present value of some amount. So I'm setting up this spreadsheet to solve what the cash flow diagram we have. So there's year 0, 1, 2, and then I'll continue the pattern on down through year 5. The amounts are negative 60,000 was how much we pay at time 0, and then we get $16,000 a year in revenue because we bought that equipment and it allowed us to do some jobs. Now I'm going to use the PV function. So equals, and then I type in PV, and that's one of the built-in functions that Excel knows about. As soon as I put the parentheses, it's going to start giving me hints on what it expects to see in the function. So it says, first of all, the rate. So it's expecting to see some interest rate. So that tells me I need to click up here because that's going to be the reference to the interest rate. And if I press the F4 button, it's going to anchor the reference. You know those dollar signs that makes it so that even when you drag the cell down, it continues to look in the same spot? So I'm going to press F4. Now the reference is anchored. Now for NPER, that means the number of periods. And so in other words, how many years is it taking to get it to the from the future to the present? So that's the year that we're on, is the number of periods. And I'm not going to anchor that reference because as I drag the function down, I want it to continually update which year it's looking at. Okay, so I'll put in a comma. And now the PV function is asking, what is the payment? Now this is where we have to be kind of careful because the way that we're treating the $16,000 and the $20,000, we're treating those as individual single amounts. We don't want it to repeat. We are treating those as future values. And so I'm going to skip over the payment field by just putting in another comma. So I didn't put in a payment, but for the future value, I want to put the negative of this amount. And the negative, I've already mentioned the reason for that. It's because if I don't, then it's not going to return the correct sign. Now Excel does some goofy things, and one of them is it thinks that negative amounts should be red. And so I want to change the formatting from currency. If you just click on the default currency formatting, then it'll take it away the parentheses and the red text and all that. I also don't necessarily need to see it to the penny, so I'm going to decrease the decimal just so that it's a little bit less busy. So now as I drag that formula down, it's going to apply the same calculations to each of the years. Now this is interesting. Is there an error? Why is it that 16,000 in year 5 is only worth 9,000, but 16,000 in year 1 is worth 14,000? Why is that amount going down? I'll give you a hint. It's not a mistake. It's doing the right thing.
The interest.
Okay.
The interest, how many years?
Okay. That's right. Did somebody else have an additional comment or a different take on it? So remember, these are present values. So what it means is, here's the language interpretation. $16,000 in 5 years discounted to the present is only worth $9,000 in today's terms. So it's so far in the future that it doesn't have much value today. Remember, money now is more valuable than money in the future because of inflation. And so in 4 years, that's fewer years of discounting. And so the $16,000 in 4 years, if you move it to the present, it has a value of $10,000. And so the closer you are to the present, the less discounting has to occur. And so $16,000 only 1 year away from the present is worth pretty close to $16,000, or at least much closer than these amounts that are much further in the future. Okay, so let's add up, let's do the sum of these present values of the amount. So I'm going to use the sum function and highlight all of this, and if we did it right, we should get the same amount that we calculated by hand. And that hand calculated amount said that 23, 23, and 20 cents. Let me show those cents again. Pretty close. The reason for the difference is that we were using the table lookup factors, which are only accurate to 1, 2, 3, 4, 5 digits. Whereas when you're doing it in Excel, it's accurate to, I don't know, something like 16 digits. It's more accurate. So it's correct. So that's the answer if it's 12% interest. What about if it's 10% interest? All right. if you need to borrow money at 10%, would this project be acceptable? If your minimum acceptable rate of return is 10%, and you borrow the money at 10%, then this project would be acceptable because the present value is positive. But if you have to go to a bank and they charge you 12%, should you do the project? No, because it means you're losing money. You're going to be losing money on the project. So here's the thing that we want to do. We want to find what interest rate causes this sum to be 0. So it's somewhere between 10 and 12%. So what about 11? We've already gone too far. So now it's down in the negative territory. What about 10.1%? 10.2%? 10.3? This is getting tedious, right? Is there a better way? There has to be.
Could you make the sum equal to 0, and then it would just kind of,
What if I just do this? 0.
Yeah.
It didn't change the interest rate.
Alright.
But you're on the right track because what we're looking for is we want the sum to be 0. That's our goal. So here, data, what if analysis, goal seek is a way of doing that thing that you just mentioned. So we're going to tell it our goal is for C11. So the sum should be 0 by changing the interest rate. So what we're doing is we're giving it permission to monkey around with one of the numbers in that spreadsheet we set up until we get the sum equal to 0. So as soon as I click OK, it's going to do that. It's going to happen really fast. All right. So the answer is 10.425. Boy, that's a lot of precision. So that's the interest rate that makes it so the inflow and the outflow is in equilibrium. And that's going to be really important later on when we start analyzing, should you do a project, should you not do a project. In other words, what this means is this is the limit of the interest rate that you can have acceptable and still break even on the project. Any interest rate more than 10.4% and you're going to lose money on the project. Any interest rate less than 10.4% and you're going to make money on the project. Okay, so that's the demonstration I had in mind here for using this. The sum of the present value of the amounts is equal to 0. So here's the sum of the present value of the amounts. So here was the amount column, was just the cash flow diagram translated to the spreadsheet. Then we did the present value function, and then the sum of the present values. And we wanted the sum of the present values to be equal to 0 by changing I. That's a lot. You just drank from the fire hose. But you'll get a lot of practice with this stuff in the future. This is just the first demonstration. Any questions about what I did? Yeah.
So this isn't a direct question about what you did, but when you were talking about, you know, your minimum, was it minimum rate of return? Where,
Yep.
The rate, you don't want to break even with your loan.
Yep.
Versus what you're taking in. Now later, when we account for things like man hours of work and that sort of thing, will we then be looking at a minimum rate of return that's like adjusts for the costs of like the things that aren't directly like loan related, like how many light bulbs do we have to set up in this, and how many people do we have to see on the scene? Is that gonna?
Good question. Yeah. So he's asking about what about the costs, you know, like the variable costs, and those costs. What you should do is reflect those in the profits that are left over each year. So like each of these arrows, what it represents would be your net revenue. So it would be the money that you got for doing the work minus the labor costs and the rent and fuel and calibration of equipment and all that stuff. So that's how you'd make sure that you're actually talking about profits.
Right.
Is that each of these arrows in the future would be the costs would have been taken into account.
So then you can kind of consolidate it into one dashboard as opposed to having like 40 little ones.
Right. That's right.
Okay. Awesome.
There's one more function I want to show you. You know, there's always an easier way with Excel. There's always an easier way. And this thing that I did, it's good for us to see the individual contribution of each year. But if all we really want to know is the rate, then we can use the function that's called the rate function. And so let me show you how to use the rate function. So we've seen PV, but there's another function called rate. And so I'm going to just do that function here. So equals rate, and a parentheses, and it starts giving me hints about what it wants to know. So NPER. Does anybody remember what that abbreviation stands for?
Number of periods.
Number of periods. Right. So I'm going to just type in the numbers this time. How many periods are there? 5. Okay. Payment. Now this time it is a recurring payment each year of 16,000. So I'm going to type in 16,000. That was the recurring payment. Now what is the present value amount? -$60,000, and then I can close the parentheses. So what it's going to do is it's going to find what interest rate brings equilibrium between the future amounts and the present amounts for 5 years, 10%, and if we have it show all of the precision there, we'll see that it's the same 10.425 that we calculated the long way. So equals rate is that other function. Okay, so we got through question 1 of the in-class exercise, but not question 2. I know that some of you have started on it already, but when we pick up on Wednesday, we're going to do that. One last reminder, tonight is the presentation from DOH at 5 o'clock, and on Wednesday you need to submit your homework assignment before class on Wednesday. I'll see you then.